Hello, AP Stat students. Today we are looking at dependent events. Okay. Remember, we've looked at independent and dependent events before. Independence means when two events do not have an effect on one another, and dependent events is the opposite of that, when one event does have an effect on the other. In statistics, this is also called conditional probability. So first, we have a new notation. This vertical line right here stands for the term given. Okay, and what that means is we're trying to find the probability of event A given that event B has happened. And we'd only be worried about this if the two events are dependent, meaning that if A has happened, it has some, or if B has happened, it has had some effect on A happening. So this ends up giving us two new probability rules. We have first the general multiplication rule for any two events. And this will work whether they're independent or dependent. But basically the probability of two events happening, A and B, is equal to the probability that A happens times the probability that B happens given A has taken place. So this given A right here just stands for kind of a reminder that, hey, A happened, it may have affected B. And this is especially true in places or in incidents when we're drawing things without replacement. Which means that if we were drawing marbles out of a bag and we drew a marble out and didn't put it back in the bag, it changes the probability of the next marble. Or taking cards out of a deck of cards, if you pull a card out randomly and don't put it back in the deck, it's going to change the probability of the next card. Okay? So we have to be careful about that. So that given, the vertical line just says, hey, remember, A has already happened. Take that into account when you're figuring out B. And then we have another rule called the conditional probability rule. And this is what's the probability of A given B. And it's simply the probability of A and B divided by the probability of that B happened. Because remember, we already know B happened. So we already know that of our choices, the only choices we have are the probability of B. Okay? And then we want to know what's the chance of A and B happening at the same time. So we will demonstrate this with a couple examples. Tree diagrams are an excellent way to solve conditional probability problems. So let's look at this one. It says, in a certain college, 25% of the boys and 10% of the girls are on scholarships. The girls represent 60% of the student body. So of course, by the complement rule then, 40% must be boys. Okay. So we're going to draw a tree diagram of that situation. We'll let B be boy, G be girl, and then S will be scholarship, and S with a superscript C will be that you're not on a scholarship. That's the complement. So first thing that happens is you are a boy or a girl. So we'll do boy up here, girl down here. And we already know that in this population, the girls represent 60%. And the boys represent 40% of the population. Now, boys and girls can get scholarships or not get scholarships. And that can happen to either one of them. Okay, and from our instructions, it says 25% of the boys are on scholarships. So if you're a boy, you have a 25% chance of being on a scholarship, which means there's a 75% chance you're not on scholarship. And for the girls, 10% of them are on scholarship, which means that 90% of them are not. Okay, and we can find the probability of going down any set of branches by just multiplying the probabilities on those branches. So for instance, if I want to know what's the chance of being a boy and on scholarship at this school, I would take 40 times 0.25, which is 10%. If I want to know what's the chance of being a boy and not being on scholarships, that would be 40 times 75%, which would be 30. If I want to know what's the chance of being a girl and on scholarship, that would be 60% times 10%, which would be 6%. And if I wanted the chance of being a girl and not on scholarship, that would be 60% times 90%, which is 54%. And if you add all those up, that adds up to 100%, so that's everything that could possibly happen. Now, let's go through some of these questions. It says, if a student is chosen at random, find the probability of the following. B, that they are on a scholarship. Well, there's two ways you could be on a scholarship. You could be a girl on a scholarship or a boy on a scholarship. So I would add up 10 and 6%, which means that 16% of the student body overall is on a scholarship. C says that the selected person is a male given that someone on scholarship was selected. So here's my statement. I want the probability that you're male given, remember given stands for that vertical line, that someone on scholarship was selected. So what do I know? Well, I know that someone on scholarship was selected. So that means I know I'm in that 16% of the people that were on scholarship above, because that's what we just found out. The probability that you're on a scholarship was 16%. And now I want to know what's the probability you're male in that situation. So of the scholarship people, remember, 10% of them were male. And I get that up here on the, on the diagram, I circled it in green. Those are the males who are on scholarships. So that is 10%. So if I divide those, 10% divided by 16%, I get 0.625. So basically, if you tell me someone's on scholarship, there's a 62.5% chance that that person's male. Okay, so just think of the given as something we know ahead of time. So in this case, we knew that someone on a scholarship was selected, so I know I'm in one of those 16% of those people. And then what's the chance that you're male in that group? Well, that would just be 10 out of 16. So one thing that's important here, when you're using this formula, that the A and B, the and stands for going down a certain branch of the tree diagram. So when I say A and B, it means I'm going down branch A and then branch B. Okay, so it's the result of that, of multiplying those two branches together. And the probability of B, that could be more than one branch, because like in this situation, there was two ways to be on scholarship, boys and girls. I had to add those together. Now, D says, given that the person is not on scholarship, find the probability the person's a girl. So, given not on scholarship. So in my equation, what I know is that the person's not on scholarship, and I want to know what's the chance they're a girl or a female. Okay, so when on these given problems, the denominator is always what we're given. So I need to know the probability that you're not on a scholarship. And I'll change my color here. In the tree diagram, the not on scholarship people I'm circling in yellow. How do I know that? Because those are the branches that ended in no scholarship. So the bottom would be 30 plus 54. And then I want to know what's the chance you're a girl and not on a scholarship, because that's the numerator. So that would be going down the girl branch and the not scholarship branch, so 54%. So it's 54 over 84. Which is 0.64. Okay, I wanted to point this out, that notice, change color one more time here. Notice that when I'm finding the chance that you are not on scholarship, one of the numbers was 54%. Okay, and notice that number ended up being in the numerator. So that happens here a lot. If you looked at the previous question, I had wrote down 16% as the numerator, but that was actually the 10 plus the 6. That the chance of being a boy on scholarship and then the chance of the girl on scholarship. So notice the 10% was there too. So on these, you'll always find a part of the denominator in the numerator. So what we learned from D is that if you tell me that you have someone that's not on scholarship, there's a 64% chance that they're a girl. I think that makes sense to the problem if you think about it, because such a high percentage of the girls aren't on scholarship at this college. Now we can also do these using a table. Okay, this is a really nice way to look at conditional probability problems. So you can see the two-way table at the right displays the members of the U.S. Senate in a recent year. If we selected a U.S. Senator at random, what's the probability that we choose a Republican? Well, that's an easy one, because probability Republican is just 54 out of the total. So 54% chance. And that's a marginal distribution, if you remember from before. I want to know what's the chance in B that you're a female. So that would be, I'm going to change colors. That would be, there are 20 females out of 100 total. So that's 20%. And C says a female Democrat. So this is the probability of being a female and a Democrat. So female Democrats are 14. So it'll be 14 out of 40. Or I'm sorry, 14 out of 100. 14%. Now, here's where the conditional probabilities come in. I want to know for D, the probability that you're a Republican, given we selected a male. So it's probability of Republican given a male. Now, in a table, when you're given male, what that means is that you already know that this person is a male. So we already know that they must be in this column. So we know if you're given a male that you must be one of these 80 people, because there's 80 males. So that goes on in the denominator. Remember, the given always goes in the denominator. And then now I want to know what's the chance you're Republican and male. Well, that's these two. Now remember, and in a table like this is the overlap of those two. So Republican and male is 48. So that's 48. So it's 48 out of 80, which is about 60%. And then we could go the other way. I'm going to change colors here and make it stand out. I don't know, what's the probability you're a female given you were a Democrat, if we select a Democrat. So it's female given you're a Democrat. So this time, what we know about this person is that they're a Democrat. So we know that they must be in this row. Okay? So we know they're one of those 44 people. And then I need to know what's the probability you're female and a Democrat for the numerator. And female and a Democrat would be this group right here. Remember, it's the overlap of being female and Democrat. That'll be 14. So it's 14 out of 44, which ends up to be about 32% if you round. Okay, so in a table, it's pretty easy because whatever's given, you just focus on that row or that column, and you know that your probability is going to be out of the total of that row or column. We can also do these using a Venn diagram. So here's our situation. It says Freezy's ice cream stand is testing out 2 new flavors, Pumpernickel Brickle and Dandy Cotton Candy. A poll conducted by Freezy's shows that 32 customers liked Pumpernickel Brickle, 58 liked Dandy Cotton Candy, and 12 liked both. And 22 liked neither. What is the probability that one of the customers liked Pumpernickel Brickle or Dandy Cotton Candy, but not both? All right, so we'll label the Venn diagram first. Let's say this one's the pumpernickel brickle, and this is the dandy cotton candy. So what do we know? 12 liked both. 22 liked neither, which would be outside of the circles. They told us that 32 liked pumpernickel brickle, but of that 32, we know 12 liked both. So that means 20 just liked pumpernickel. And then for the dandy cotton candy, we knew that 58 liked dandy cotton candy, but 12 liked both, which means there were 46 that just liked dandy cotton candy. So now the question is, for A, or the first question was, what's the probability that one of the customers liked pumpernickel brickle or dandy cotton candy, but not both? So that would be 20 plus 46. So that would be 66. Oops, wrote it in the wrong spot. And there were 100 people altogether. So about a 66% chance that somebody liked pumpernickel brickle or dandy cotton candy. Remember, for or, we don't count the middle, the overlap. So B says, find the probability you like pumpernickel brickle given you liked dandy cotton candy. So I want to know, what's the probability you like pumpernickel given you like dandy? So my numerator is going to be people that liked pumpernickel brickle and dandy cotton candy, which would be 12. And my denominator would be just how many people liked dandy cotton candy. So I'd have to add 12 and 46, which would be 58. So 12 out of 58 ends up to be 21%. So we knew that the person liked dandy cotton candy, which means if you look at the Venn diagram, we know they were in this circle. So that's how I got 58 on the bottom by adding up the two parts of that circle. And then I want to know, what's the chance you liked pumpernickel brickle? Well, in that group, only these 12 liked pumpernickel brickle. So it'd be 12 out of 58. So the given in a Venn diagram problem limits you to one circle in the diagram, okay? Or it limits you to whatever area that the given is mentioning. C says, find the probability that you like dandy cotton candy given you like pumpernickel brickle. So this time we're going dandy cotton candy given pumpernickel brickle. So this time my given is, we know the person likes pumpernickel brickle, which puts you in the P circle. So it's all of these people. So that would be 12 plus 20, which is 32. And then I want to know, what's the chance you like dandy cotton candy in that group? Well, it'd be only 12 of those like it. So it'd be 12 out of 32, which gives us 38%. Okay, so in the given in a Venn diagram situation limits you to one of the circles in the diagram. And then one final example. We'll do this with cards. So Joe has a deck of 52 playing cards. There are 4 suits: diamonds, hearts, clubs, and spades. Hearts and diamonds are red, clubs and spades are black, and then each suit has the numbers 1 through 10, and then a jack, queen, and a king. So that's 13 per suit. Okay? So it says Joe selects one card, records its suit, and sets it on the table. Then he draws a second card from the deck. So this would be called without replacement, which means that the situation we're looking at is dependent. Okay? Drawing one card out and not putting it back in the deck changes the probability of the next card. Okay? So here's the question. What's the probability the first card is a heart and the second card is black? So we're going to use our formula. The probability of A and B happening would be the probability of A times the probability of B given that A happened. To put that in terms of this problem, it would be the probability of a heart and then a black card would equal the probability of a heart on the first draw times the probability of a black card given we got a heart on the first card. So obviously, it's important to think about the given because once I've taken a heart out of the deck, it's going to change the probability of the next card. So what's the probability of drawing a heart? Well, we said hearts make up 1/4 of the deck, and we could call it 13 out of 52 cards, which is 1/4. Then I'm going to multiply that by the probability of drawing a black card given you drew a heart. Well, since I drew a heart, it means there's only 51 cards left in the deck, and I need to know how many of those are black, and half the deck is black, so that would be 26. And that original heart I drew was red, so I don't have to count that. So it'd be 13 over 52 times 26 over 51. So it'd be 338 out of 2652, and we can divide that, and we get about a 0.127% chance. So about a little, almost just a little under 13% chance that if you drew of drawing a heart and then a black card. So this is a good example of why we need this given, okay? Because when we take a card out of the deck, our deck drops one card, right? And so instead of choosing out of 52, once I've drawn the first card, now I'm only choosing out of 51, okay? So that's why we need to study dependent events, because when events are dependent, one event occurring affects the next, okay? And that's a super big hint that you're looking at dependent events when you do things without replacement. So good luck with dependent events.